Yeah, we have taken up. I asked him this by golly, I am. No, like what a response.
Yeah, I didn't get you.
Well, they switched their.
Congrats on what? Thank you. That's a little bit. A little bit.
Thanks.
My 356. Every time I try to reference any specific type of data type that I need, it just says it's well.
Yeah,
I know. I don't know what to do. Did you look at that thing on null the variable? Yeah, I did that. On the class. On like the class for it. Yeah, I did that. I mean, you have to do other places in the class. Oh, okay. Maybe that's it. Anytime a value crosses the null, I can reference it. You have that default value for it. But is it getting any data from that? I have not checked for that. Set up breaking. With like right at the system, see if it has any in it or after you like it, you know. Go to the yeah.
Okay.
I tried just assigning to like the stocks the case and stuff, and it did that. I can look at one spot. I have like the for instance, like for each state, I have like the specific state. We want to switch it to different one. That one date. Yeah, I put it to dates. That's right. Like the historic value of the state. Yeah. Yeah, all about it. Yeah, yeah. He was just the one who didn't go more than so much.
Okay, so this chapter is talking about applications of Fourier transforms and Fourier transform theory. We talked about modulation last time. specifically a form of amplitude modulation called double sideband modulation. Still hoping my projector decides to come off today. Because I have some stuff I want to project up here, but if not, we'll make do. But today I mentioned that that's what we talked about last time. It's conceptually simple to generate. Really just take the signal off of a microphone, multiply it by a high frequency cosine. That's all that's necessary to translate the signal up to a very high frequency then and transmit. And that is used in some communication systems. One of the problems with it is that the receiver has to be pretty expensive. It has to use what's known as a synchronous receiver. You have to generate that same cosine wave at the receiver and do the multiplication again at the receiver. So standard AM radio, at least on the receiver, there's a much simpler demodulation or detection process that's used for standard AM radio. So continue talking about the modulation, where last time we mentioned that we're not going to get into FM or phase modulation, but this is the carrier, and with the double sideband modulation method we talked about last time, you multiply the carrier by your low frequency signal. And this is called double sideband modulation, where X of t here is your low frequency signal or your message. Okay, there's a slight modification for what's called AM radio, and it's actually pretty closely related to double sideband. So this is all that's done for a standard AM radio transmission. It's actually, we just add a constant to the low frequency message. So this is the voltage coming off of a microphone. It would be adding a DC bias actually to the signal. We require that A plus XT is greater than 0. That means that the offset has to be large enough so that the minimum of A plus XT is always positive. Okay, so, or it's usually stated in terms of a modulation index. If we define X min to be equal to the minimum of XT, and in most cases, our low pass signal has both positive and negative variations. It's usually centered around 0. That's the case for a microphone, for example. And so the minimum value of XT is actually negative. Usually, for most signals, it may swing between plus or minus 2 volts or plus or minus 5 volts, whatever, but the minimum and maximum values are equal and opposite in amplitude. This is showing, for the double sideband, we take X of t and just multiply by the carrier. For AM, standard AM radio, we just add a DC bias. And I'll talk more about why that is done. We require M less than 0, where M is the absolute value of X min over A. And this is called the modulation index. And you can work through the math on that, but it essentially just means so let's see, this is a segment of our low pass signal, or signal coming off of our microphone, above and below 0. A has to be large enough so that the whole waveform, A plus x of t, never goes negative. And that's being shown here when the modulation index is less than 1, that happens. Okay. When the modulation index is greater than 1, then it doesn't happen. And there's a problem with this one. We require this, that A be large enough so that A plus xt is never negative. The reason for that is, if you look at what's called the envelope of the modulated carrier. So we take this, if you remember, we multiply it by our high frequency carrier. The way we can draw that is, draw the negative of this, and then just fill it in with our cosine waveform. Well, as long as A plus xt is greater than negative, the envelope of our modulated carrier looks like A plus xt. But if A plus xt is not always positive, our envelope, our A plus xt signal would actually continue on here, but the envelope, which is following the positive peaks, would look like this. Okay. Would be a distorted version of our waveform. Okay. So this is why we have that requirement. The reason is we're going to use an envelope detector that just follows the peaks to recover our low frequency signal. And if this condition isn't met at the transmitter, then we get a distorted version of our message signal. And I'll talk more about that right now. A envelope detector is nothing more than actually a half-wave rectifier. So it's a little bit more than a half-wave rectifier, but not much. You guys built half-wave rectifiers usually back in the first semester of your electronics. So last semester, I guess. So if you remember a half-wave rectifier, they're typically with a sine wave coming in. You run it through the diode actually removes, with a half-wave rectifier, it removes the negative portion of the sine wave, and then the capacitor actually then follows the humps. You charge up the capacitor here, it starts to discharge, but you get another voltage hump, so it'll charge up the capacitor, and so you get something like DC out. Okay. This is pretty much the same, except with our AM waveform, our amplitude is constantly changing. Coming out of the wall, the amplitude is fairly constant, so you get a DC, get a D level from a half-wave rectifier. This is the same circuit as your half-wave rectifier. But now, what our capacitor here charges up, discharges, charges up, discharges. It will follow as our peaks change. It will, our capacitor voltage will follow those peak voltages, and that's exactly what we want to do. Now there is, you have to pick this time constant appropriately. You don't want the time constant so long that it averages out over the waveform. You actually want it to follow the peaks, but you don't want it to be so short that it discharges too quickly either. Okay. So, but usually that's a pretty easy thing to do because the time constant really just needs to be longer than the period of the carrier, which is really short. and shorter than the period of the highest frequency in the message. So there's quite a range to play around with there. But so what this allows you to do versus, the last time we looked at what a AM receiver had to do, we had to have this analog multiplier in the receiver, and we also had to recover the carrier. Those are expensive techniques. I mean, you can do that. Okay. This AM radio is just a few pennies. Okay. So this is why AM radio was so popular. It was the first modulation method. But instead of spending, instead of families spending hundreds or thousands of dollars for radio receivers, you could really get an AM radio receiver for just a few dollars because it was so inexpensive, the fact that we could use this envelope detector. Now the technique actually requires transmission of more power. So it's not as efficient as double sideband because we're adding this DC offset that requires more transmitted power. So this technique actually uses more power, but that's power expended at the radio station, and the advertisers pay for that power, right? So double sideband is more efficient in terms of power usage, but standard AM radio is so cheap because you can use envelope detection on it. And it was just a matter of just offsetting the waveform in order to be able to do that. This is showing a very special case of what's called tone modulation, where the low frequency message is actually a 1 kilohertz sine wave, and then on a 10 kilohertz carrier. So you could generate that in MATLAB pretty easily, actually. But what's one of the nice things about AM is that you can really see the low frequency message, in the modulated carrier. Okay, you can see it on an oscilloscope. That's not the case with techniques like FM or phase modulation. Now, it does have a DC bias when we recover it from the envelope detector, but that's easy to remove with just a capacitor, right? You've seen how to remove a DC bias. So we can, it has this A offset when we recover it, but we can remove that pretty easily to recover our low frequency signal. Okay. So, what does the spectrum look like? The spectrum of AM is similar to that of DSB. So now our modulated waveform, if I multiply the cosine through here, I'll have A cosine 2 pi FC of t plus xt cosine of 2 pi FC of t. Well, this is my double sideband modulation, right? Multiply xt. And what that does is just translates the spectrum and frequency. And then this is the new component that's present in AM radio that's not present in double sideband. But this is nothing more than in the frequency. This is just, it's a sinusoidal time. It's just an impulse and frequency. So I won't write down the formula for the spectrum, but it would be just our double sideband spectrum, which we had last time, plus a pair of impulses. You can see that here. This is double sideband modulation of that 1 kilohertz tone. Actually, I guess it's not 1 kilohertz here because they're just modulating to 50 hertz. So if this is really seconds, it looks like it has a period of a second. So it looks like a 1 hertz tone imposed upon a 50 hertz carrier. Okay. And now with the tone, you know, double sideband, if you looked at the low frequency spectrum of a 1 Hertz tone, it's got components at +1 and -1. We multiply that by our 50 Hertz carrier, what we get is 2 impulses at 51 and 49. Okay, that's what we talked about last time. And that's what's showing up here. We get these 2 impulses at 49 and 51 Hertz. The only difference with AM, it's the same signal with the DC offset now, and so it looks different. Here, our cosine wave is actually this. Right? Now we've shifted that up, so here's that same waveform in AM. In AM, in addition to those 2 impulses due to the 1 Hertz message, we also have an impulse at 50 Hertz due to this term. This would give us impulses at ±50 Hertz. That's showing the double-sided spectra there. So the spectra looks similar, but if you look at this in a spectrogram, you'd actually see those impulses pop up in AM, and they wouldn't be present in double sideband. I mentioned also that there are techniques that, you know, in our real signals, we have this symmetry. So there's some redundancy there, so we can save some bandwidth by actually using just single sideband modulation. And when we translate this up to 50 Hertz or whatever, we get both sidebands. That's what's called double sideband. But then there are some single sideband methods where we can filter one of the sidebands out and actually use less bandwidth. And those require a more expensive receiver that can't use envelope detection on those. Those require a more expensive receiver. I mean, they are used in practice because they're very power efficient. Okay, so power efficiency is important for portable transmitters, right? You wouldn't use standard AM radio with a portable transmitter. There you want to be worried about, you know, battery usage in your portable device. But I want to talk a little bit more about that multiplying by a cosine. It's called mixing or frequency translation. So the idea in our Fourier theory tells us this: by multiplying a modulated signal by a sinusoid, I've just been using cosines, my examples, but sine would work as well. We can shift the spectrum in frequency. And what we've been doing is shifting our low pass signal up to the carrier frequency. But there are applications, and we'll see one today, a super heterodyne receiver, where you may want to shift to yet another frequency. All you need to do is multiply by cosine again. So look at, this is our double sideband signal. It would work with AM, it works with FM, it works with television. This technique is used throughout modern communications. Okay, but to shift the spectrum, so here it would be centered around F1. Take our low pass signal multiplied by a carrier that's operating at a frequency F1. It translates the spectrum up around F1. To shift the spectrum to F2, we just need to multiply this signal by cosine of 2 pi F1 plus F2 t. So y of t would be y of m t cosine of 2 pi F1 plus F2 t. And almost all of communications, you really only need one trig identity, and that's cosine A times cosine B. And that gives you 1/2 cosine of the difference plus 1/2 cosine of the sum. So we have that here. We have y of m has this cosine in it. So if I use that trig identity, y of t is going to be 1/2 x of t. Now cosine of the difference is 2 pi f2 of t, right? Because this has got a 2 pi f1 of t plus 2 pi f2 of t, so I subtract the 2 pi f1, and I'm left with just the 2 pi f2 of t. And then I get 1/2 xt cosine of the sum. So I'm going to have 2f1 plus f2 of t. So what does this look like? This looks like xt translated to f2. And this part looks like xt translated to 2f1 plus f2. Well, this is the part I wanted, right? I was interested in just translating to f2. Well, it's easy to filter this part out. I'll just bandpass filter around f2. So the next step is bandpass filter at f2, and my output would be bandpass filter around y of t, and I get 1/2 xt cosine of 2 pi f2 of t. So essentially all I've done with this technique is change the carrier frequency. It's still a double sideband modulated signal. It works the same just for AM. If it were an AM signal that I multiply by another cosine, again, it just shifts the spectrum, and I could still use envelope detection on the AM signal. This process of multiplying by a cosine is called mixing or heterodyning. You might think it's called frequency multiplication, but that's actually something different. So the process of multiplying by a cosine, it's called mixing or heterodyning, or you call it frequency translation. You could also achieve the same result by actually multiplying by cosine of 2 pi f1 minus f2. It doesn't, because you get the sum and difference frequencies out, and then just filter around f2. And I'm not going to go through the math on that. But if you multiply by f1 minus f2, then the sum would be at 2f1 minus f2, but the difference would still be at f2. So, and that's what this is showing on my screen, but that's what this is showing here. You have an so we have a modulated input, that's with a carrier frequency at f1, and we multiply it by a sinusoid that's either with a frequency of either f1 plus f2 or f1 minus f2. Doesn't matter, both would work. And then what you get out is two components. One component at f2 though, and we bandpass filter around f2 to pass that through. And so essentially we've changed the carrier frequency. Now that is used in modern radio receivers in what's called a super heterodyne receiver. Super, or often just called a superhet. And this technique is used in all modern radio receivers that I'm aware of. I mean, you might buy a really cheap AM radio that doesn't use this technique, but almost all modern receivers use this. So now, kind of led you to believe that, you know, the way you do channel selection or station selection is you bandpass filter around the station that you want. Filter out everything else. I mean, that would kind of work, right? At our AM receiver, we turn a tuning knob that's adjusting the center frequency of a bandpass filter to pass through the station we want to listen to, envelope detect that, and we're all set. I want to listen to a different radio station, turn our tuning knob, changes the center frequency of our bandpass filter, pick up a different station. Early receivers used that technique. Used a tunable bandpass filter to select a station. And so pictorially, this triangle represents an antenna. And then coming off that, we have a radio frequency signal. It's a bunch of different stations that we're picking up. And then the idea here is that we've got a tunable bandpass filter. So I'm going to show that it's tunable by putting an arrow through it. So we can adjust the center frequency. Then I'm going to draw a little tuning knob here. Okay. And then, so we get the station that we want. Okay. And then, so that's the station that we want is coming out of our tunable bandpass filter. And then we envelope detect. And then there's typically an audio amplifier then with an adjustable gain. It's connected to your volume knob and then goes out to your speaker. Okay, that's supposed to be a speaker, that thing at the very end. And this is called a tuned RF receiver, okay, or just a TRF. Unfortunately, it's not easy to build a high quality tunable bandpass filter. So in the early radio days, they would often have 3 different knobs that you were adjusting to try and tune in a station. One that might be a cutoff frequency for a low pass filter, so that you're shaped like this, and then you're passing through all the stations below a certain frequency. Then another one that might be a high pass filter, so you're passing through all the stations above a certain frequency, and you're tuning these knobs until you get the radio station that you want to listen to. It was actually pretty tedious. You know, it could often take 15, 20 minutes to tune in a radio station. I don't know, you may have seen these things in pictures, but you know, eventually you'd give up and go play horseshoes or something. I don't know, whatever they did, checkers, horseshoes. So it's not fun. Again, the issue is building a high quality bandpass filter that has enough selectivity to filter out adjacent stations and pass through the one that you want to listen to. I'm going to try and draw some pictures here of, these are in frequency in kilohertz. I'm going to just draw different spectra representing different radio stations. So it doesn't really matter what you draw. Okay, just 4 different pictures there. And then, so this would be the spectrum of the signal coming in off the antenna. You know, those 4 different radio stations. Again, there's a bunch of different radio stations. Well, here's our frequency response of our bandpass filter. Now this is adjustable, so this can move up and down, but I want to listen to 1020 kilohertz. And then, so we know, you know, in the frequency domain, I multiply the Fourier transform of my input times my frequency response. So I've drawn, you know, kind of an ideal bandpass filter here. But then, so then what we would get out is just the one station we're wanting to listen to. Okay, at 1020, all the others would be filtered out. And then I'd envelope detect that, you know, for a standard AM radio. Okay. Modern receivers actually use a tunable oscillator instead of a tunable bandpass filter. It's actually a lot easier to build a tunable oscillator than it is a tunable bandpass filter. And I'll draw the picture here. Modern receivers use a tunable oscillator and a mixer and fixed bandpass filter to select the station. So the idea here is we can build a really high quality bandpass filter. It only has to operate at one frequency. So this is the block diagram of this receiver, YRF of T. But now, when you adjust your tuner, you're actually changing the frequency of this local oscillator. So the local oscillator frequency would be the desired carrier frequency you want to listen to, the station you want to listen to, plus, I'm going to call it FIF, it stands for intermediate frequency. But remember what we just had here, I said that if I want to translate FC, for example, to FIF, I just mix the station at FC with another frequency that's FC plus FIF or FC minus FIF. Remember, we can use either. I just drawn the plus here, no particular reason. Now we have next a bandpass filter that just works at this intermediate frequency. It's not tunable at all. And then Y2 of T, we then envelope detect audio amplify and speaker. And this is called a super heterodyne receiver. It was developed by somebody Google this for me. His name was Armstrong. So you probably just Google superheterodyne and Armstrong. I want to say George Armstrong, but I don't think that's correct. But back in, I think he developed this back in the 20s or 30s. And he also developed FM radio. So, but in FM radio, with his FM radio, he got into a dispute with David Sarnoff, who was the head of RCA at the time. And RCA had all these AM radio stations that they owned across the country. And Armstrong was trying to push FM. And then Sarnoff fought back because he didn't want any competition for his AM radio stations. And Sarnoff had a lot of money. RCA had a lot of money. I think Armstrong committed suicide in the process at a fairly young age. Connor, did you find it there?
Yeah, his name's Edwin.
Edwin Armstrong.
It says that he didn't make the superheterodyne receiver.
What?
It says there was controversy, and now the patent's credited to a French engineer.
Oh, okay. Well, I think Armstrong developed it here in the U.S. Whether he stole it from the French guy or developed it independently. But he also developed FM, and I think walked off the 13th floor of a hotel, something at, I don't know, I think he was in his 40s.
He died at 63.
63?
Yeah.
God, that's older than I thought. When did he did something, what did he develop when he was an undergraduate? That was like, I think it was at Columbia, maybe I'm embellishing this. I think he did, was that positive feedback he worked on? Yeah, I think that's a positive feedback. Regenerative circuit he developed when he was an undergraduate at Columbia. Yeah. So, but actually, he did a lot. It's unfortunate that he got into this dispute with Sarnoff. Okay, so my stories are a lot better when you guys can't fact check them. Let's start banning phones, I guess. A standard intermediate frequency of 455 kilohertz is used in AM radio. And just meaning that you can go and buy off the shelf a bandpass filter that's designed to operate at this 455 kilohertz. FM uses a similar technique. They use a higher intermediate frequency because of the higher bandwidth of FM. I think they use 11.7 megahertz as the intermediate frequency for FM, but you can Google that too. I think it's 11.7, 11 something, 11.5. Just intermediate frequency FM probably would get you there. Most modern receivers actually, again, use this technique. FM uses a different detector. So I'll try and draw the pictures here again. So this is, did you find it?
It says 10.7.
10.7, okay. That wasn't a lie, that's just poor memory. I'm going to draw the same picture, trying to figure out what's going on now. 10:30. Now, I'm going to assume we want to listen to the same radio station at 10:20. So our local oscillator should be our carrier frequency plus our intermediate frequency. So 1020 plus 455 or 1475 kilohertz. So when that is mixed with our RF, we'll get out the sum and difference frequencies in each case. Okay. I'm only going to look at the difference frequency. The intermediate filter will actually filter out everything else. But the difference between 1475 and the 1020 is 455. So after this mixer, our station at 1020 is now at 455. Our station at 1030, the difference would be smaller, so that this actually gets reversed, 445. This one then would be at 465. And that one would be at 475. Okay, so this is what I call this. This is Y1. Y1 of F. But now my bandpass, and these things move now. When I want to listen to 1030, I would adjust my local oscillator to 455 above 1030. And then 1030 would appear here at 455. If I wanted to listen to 1000, adjust my local oscillator to 1455. And the station at 1000 after the mixing would appear at 455. So my tuning knob now is adjusting the frequency of this oscillator. Now my bandpass filter, it's a high quality bandpass filter designed to operate just at the one frequency, does not have to be adjustable. And what we get out is the product of these two. And so we get our, so coming out of this, Y2 would always be a signal at 455 kilohertz. Okay, regardless, but it would change as we tuned our radio. So this would be Y2 of F. Any questions on that? It's pretty cool, actually, how it works. So this is almost as good a picture as I drew. Here it actually shows the tuning knob adjusting the center frequency on a bandpass filter here at the front end. That's not where the channel selection is done. It's part of AM radio. It's because the AM radio band is so wide, it has to eliminate what's known as an image frequency. Because you get the sum and differences, you can actually get two different channels that actually appear at the intermediate frequency. So this is present. I ignored it. The channel selection is actually done by when you turn the tuning knob, you're adjusting the frequency of this local oscillator. They also show a radio frequency amplifier that I didn't show in my diagram. But coming in off, in this case, this is a 1 megahertz, that would be 1000 kilohertz. We want to listen to a 1 megahertz, so our local oscillator would be 1455 or 1.455 megahertz, so that when we mix, that station would be translated to 455 kilohertz. And then our intermediate frequency bandpass filter would eliminate it. And then here's our demodulator for AM radio. That's an envelope detector. There's one other thing that I wanted to mention that I think I kind of talked about is this idea of this mixing. Another application of this mixing is to translate stations to different carrier frequencies. So we have all these radio stations floating around out there, all these television stations floating around out there, or on a piece of coaxial cable. It can carry literally hundreds of different stations or thousands of different stations. Here they're showing using a wireless system and using a spectrum between 1 gigahertz and 1.01 gigahertz or 10 megahertz bandwidth to carry a number of different voice channels simultaneously. So this might be something like a microwave link that would carry, I think it's about 2,500 different voice signals here in this 10 megahertz band. I mentioned that they show here that this is a 3.5 kilohertz width. That would be typical for voice, not music. And then there's typically a little space between them so that you can filter them out. But each of the different voice signals is translated up to a different center frequency, a different carrier frequency. And we can sum them together and then transmit them, via antenna, put them on coax cable. At a receiver then, we can filter out each one of them. You could use bandpass filters like this or actually use the super heterodyne technique. Bandpass filter to separate out all the different voice channels. Then we have to demodulate by multiplying again by the same frequency to recover X1 of T. But it really is that simple. Most of modern communications is just multiplying by high frequency sinusoid to shift the frequency of the spectrum. And FM is a little more complicated. You'll learn about, those of you in electrical engineering will learn about FM when you take the communications course next year. Okay, we got one more topic to cover that we'll cover on Friday. That's on sampling. So we'll start this process of analog to digital conversion. And we'll continue that in 311 next semester, actually. But that's it for today.